So this is the Waves homework booklet question 20. So we've got a diagram showing a section of a typical step index optical fibre. That's the sort of optical fibres that they always ask about, used for communications. So what have we got? We've got a light ray coming in at 14.1 degrees. It carries on in the core at 9.54 degrees and it reaches this point X, the normal. The rest of the stuff I've added on answering the question. First question, show the refractive index of the core is 1.47. It's show question, start from the beginning. N1 sine theta 1 is N2 sine theta 2. N1, we're starting out in air, so N1 is 1, sine of that 14.1 is N2 sine of the 9.54. Rearrange that, gives me N2 is that number, sine of 14.1 divided by sine of 9.54, and that works out as 1.47. I don't need extra significant figures here because I'm being asked to show it is rather than show it is about. Okay, the crucial parts to getting the step were that equation and that. Ultimately, it's that N2 is sine 14.1 divided by sine of 5.54. The refracted ray meets the claw cladding boundary at an angle exactly equal to the critical angle. Complete the diagram. Now, total internal reflection happens if we are above the critical angle. So if we are at the critical angle, we get refraction along the surface. If you like, we refract at 90 degrees and we get the reflected angle. I'm going to make sure that I draw that accurately along there, and I'm going to measure that angle there and make sure I reproduce it there so it looks like that reflected ray is following the rule of the angle of incidence is equal to the angle of refraction. Bit hard to do here because it turns out this isn't drawn to scale. That's quite a lot more, or a little bit more than 9.54 degrees. But make sure that you make those angles the same and label them as being the same, which is certainly something I could have added there. Calculate the critical angle. Point here is loads of people will jump straight into trying to use sine theta c as N2 over N1, but we've been told that this ray is at the critical angle. So if that's 9.54, I've got a little right angle triangle there, or you can think of that Z angle, 9.54. Therefore that is simply 90 minus the 9.54. That's the calculation I've got to do. 90 minus the 9.54, 84.46, 80.5 to 3 significant figures. I do need 3 significant figures. All of the data I've used to that point have been 3 significant figures, so I can't justify giving just 2. Do need the 3 significant figures. Then we've got the idea of N1 sine theta 1 equals N2 sine theta 2 at the second boundary. Sine theta 2 is 1 because theta 2 is 90 degrees. So that then rearranges to sine of theta 1 is N2, and then take that under divided by N1. Or you can think, just be ready to use the equation sine theta c is N2 over N1. Rearranging, N2 is N1 times sine theta c. 1.47 times the 80.5 is 1.47. If you ended up with 1.49 there, you had these two numbers mixed up or rearranged so that they were the wrong way up. It does need to be the refractive index of what you're heading towards on the top and what you're coming from on the bottom. 9, in this case, the thing we're trying to find, in fact, N2, and that's the 1.47. 2 reasons why optical fibres used for communications have got cladding. The best 2 things: first of all, it's going to protect that core from scratches, and that helps stop it breaking, and it stops us if we hit a scratch and we don't really know what angle we're hitting at because it depends on the angle of the scratch. So it's protecting the core from scratches. The other thing the cladding does is, compared with having air immediately in contact with that core, we get a much bigger critical angle. Now, you should remember that slightly anti-intuitively, a big critical angle is a good thing because it means that I get rid of, if I go back to the diagram, I get rid of sort of sharp angle zigzaggy routes. I'm only getting rays going through that are coming at fairly shallow angles. Why is that a good thing? It means that all my routes through are very similar length. So we've only got rays with small theta, or sorry, we've only got rays with large theta. If there's a small theta there refracted, they're lost, they don't reach the far end. And if all my roots are a similar length, what that does is it reduces pulse broadening, which of course therefore means it's reducing, because it's reducing modal dispersion. And that means I can increase the rate of data transfer. I can send my pulses through more quickly because the pulses won't grow in length of time while they're travelling down, because all of the possible routes with a large critical angle are going to be of a very similar length. So that's the Waves Homework Booklet, question 20.